Okay, here's OCR 2017 AS Physics Paper 1, Breadth in Physics. Question 1. Which statement is not correct about an electromagnetic wave? It can be diffracted. That is correct. It can be polarized. That is correct. It is a longitudinal wave. Yes, because it's a transverse wave. That is incorrect. 2. A narrow beam of light is directed at the surface of a triangular prism, which is the correct diagram for the light refracted by the prism. Well, you should know that from Pink Floyd Dark Side of the Moon that it is C. But let's just see why that has to be the case. As it goes in, it has to be refracted towards the normal. So it can't be this one here because that's getting it refracted away from the normal. And it can't be this one either. This ray here is being refracted towards the normal, but then it has to be refracted again away from the normal on the way out. But this one is being refracted towards the normal again, so it has to be C. 3. Force F against extension X graphs for 4 different wires A, B, C, D up to their breaking points as shown below. Which wire has the greatest work done on it before it breaks? So work done is area under graph, so we're talking half Fx. But seeing that we're just comparing them, we can just actually take Fx. We have 1, 2 across times 1, 2, 3, 4, 5, 6. So A is 12. Okay, it's 6 if we halve it, but it doesn't matter. 1, 2, 3, 4 for B. 1, 2, 3, 4 for B. 16. It has to be B because C is also 12. 4. An object experiences two forces, 3 and 4 newtons in the same plane. The directions of the forces are unknown. What is the magnitude of the resultant force F acting on the object? So we can have the 3 newtons pushing in that direction and the 4 newtons pushing in that direction. Or we can have all the way to them pushing in the same direction. And we can have them pushing in any direction in between as well. So we're looking for the minimum and maximum. So it can't be exactly 5, it can't be exactly 7 because we don't know that that's the case. It can be 7 because they can be pushing in the same direction, but we don't know that that is the case. What is the minimum force that we can have? Well, it is going to be 1 Newton, isn't it? So it has to be C. So it's going to be between 1 Newton and 7 Newtons because either of these cases could be true and any direction as well. 5. A projectile is fired in a horizontal direction at time 0, which graph correctly shows the horizontal component of the velocity h of the projectile against time t. We know that for something that is being projected horizontally, no air resistance equals constant horizontal velocity. Has to be B. 6. A ball initially at rest is struck by a hockey stick. It leaves the hockey stick at speed v. Which quantity, together with the mass of the ball, can be used to determine v? The time of the impact? No, because we need the force in order to find out the speed. The weight of the hockey stick? No, because we don't know what force is being pushed with. The impulse of the force? We know that impulse is change in momentum. If we know the mass of the ball and we know the impulse, then we can find v. So C is the right answer. Final momentum of the hockey stick? No, because we still don't know what's going on with the ball. 7. Two forces act on an object in the same plane. Which diagram shows a couple? Well, we know that for a couple, clockwise or anti-clockwise, and they must be the same magnitude as well. So it can't be B, because that's not going to make it turn at all, because they're different forces. These two, no, it's just going to make it accelerate. It's not going to make it turn. D, again, forces are both going in the anti-clockwise direction, but they are different. It has to be A, even though they're pointing off at an angle. 8. Two resistors of resistances 120 and 500 ohms are connected in parallel. The percentage uncertainty in the value of resistance of each resistor is 10%. What is the correct value of the total resistance and the percentage uncertainty? So we know that total resistance of parallel resistors is 1 over R, that being the total resistance is 1 over the respective resistances. So we can see that it's not going to be 620, it's going to be 97. If we have a 10% uncertainty there, 10% uncertainty there, then what is the uncertainty of 1 over R? You'd be forgiven for thinking there's 20%. Question number 9, potential divider circuit with an LDR is shown below. The intensity of the light incident on the LDR is reduced. So if the light intensity goes down, that means the resistance goes up. Which row correctly describes the observed change on the ammeter and voltmeter readings? Well, let's just do voltmeter first. If the resistance of the LDR goes up, then its share of the voltage goes up as well. So that means that the voltage share of the fixed resistor goes down. So it can't be B and it can't be C. And then we know that the ammeter reading is going to be different, isn't it? Because if we're changing the overall resistance of the circuit, it has to be A. 10. The minimum PD across an LED before it conducts is 2.1 volts. Wavelength of light emitted by that is that. What is the correct expression for determining the Planck constant H? So we know that E equals HF, or E equals HC over lambda. But if we're looking for H, let's put C and lambda over the other side. So we end up with H equals E lambda over C. And I can already see that the only one with C on the bottom is D. So it has to be that one. Easy. 11. A cable is attached to an object of weight 30 newtons. The object is pulled vertically upwards with an acceleration of 6 meters per second. What is the tension in the cable? Okay, like I've said in my video on this, the tension in order to hold something is just mg. That's just the weight. But if you're accelerating upwards as well, then the tension is going to be greater. You're adding on the extra force needed to accelerate it. We know the mass is going to be that 30 newtons divided by 10. So let's say that that's about 3 kilograms. Therefore, the tension is going to be this 30 newtons. That's the weight plus 3 times 6. So that's 18. So that should give us about 48 newtons. It's D. Number 12, two filament lamps X and Y are connected in parallel to a supply. Power dissipated in lamp X is 24 watts and the power dissipated in lamp Y is 6 watts. The EMF is 12 volts and there's negligible internal resistance. What is the total current drawn from the supply by the lamps? What is the total current drawn from the supply by the lamps? So for lamp X, because we know that P equals VI, power is P times current, that means that current is going to be P divided by V, and for X that is going to be 24 divided by 12, so that's 2 amps, and for Y that's going to be 6 divided by 12, that's 0.5 amps, so altogether we should have 2.5 amps. Again, it's going to be D. 13, an object is at the top of a ramp, point P. The GPE of the object is 100 joules. So we have 100 joules at the top. The object is released from rest at P. It travels down the ramp. The kinetic energy at the bottom of the ramp is 60 joules. Okay, so we have lost 40 joules of energy, and that's due to friction. If this was frictionless, we should have 100 joules of kinetic energy at the end. Question is, what is the average resistive force acting on the object as it travels down the ramp? We know the work done is F times D, force times distance. But are we looking for 5 meters or 3 meters? It's going to be the 5 meters because we're talking about the force that's acting back up the ramp as it goes downwards. They've given us too much information. We don't need that 3 meters. So force is work divided by distance. So that's going to be 40 joules divided by 5. That's going to be 8 newtons. It is a 14. The de Broglie wavelength of an electron after being accelerated through a PD is lambda 0. The accelerating PD is now doubled. What is the new de Broglie wavelength of the electron in terms of lambda 0? Okay, we know that lambda, de Broglie wavelength, is h over mv. But we can't get the answer straight from here, can we? Because we don't have PD in here. Now, what do we know? We know that EV equals half mv squared. That is the energy supplied by the PD in accelerating it is going to be equal to the kinetic energy afterwards. So we want to put this into this mv. If I take the half over to the other side and I multiply the whole thing by m, I end up with 2evm equals m squared v squared. So therefore mv, that's the momentum, is going to be equal to the square root of 2mev. So I can pop that back in here. Lambda equals h over root 2mev. How are lambda and PD proportional to each other? We can see that lambda is proportional to 1 over the square root of the PD. So if this doubles, that means that root v goes up by a factor of root 2. That means that the whole thing goes down by a factor of root 2, and that's going to be the same for lambda. It is B. 15. The diagram below shows an object submerged in water. The object is stationary in the water. Which statement about the upthrust acting on the object is correct? It is 0. That is incorrect. It is equal to the mass of the object. Well, that doesn't make sense because mass is not a force. It is equal to the weight of the object. Yes, that is correct because we have weight pulling down, upthrust pushing back up. There is no drag because it is stationary in the water. 16. The intensity of a laser beam is 2 watts per meter squared. The cross-sectional area of the beam is 1 millimeter squared. What is the energy delivered by the laser beam in a time of 100 seconds? Okay, so we just need to find out watts first. So that means that we need to turn this into meters squared. So that is 1 times 10 to the minus 3. But that's squared because we're going from millimeters to meters twice. So that is 1 times 10 to the minus 6 meters squared. So if we have 2 watts per meter squared and then this many meters squared, that means that the power is going to be 2 times 10 to the minus 6 watts. Times that by 100 seconds, that is 10 to the 2, and we end up with 2 times 10 to the minus 4 joules. So it should be B. 17. A block moves at a constant speed up a ramp. The diagram below shows all forces. Which force does no work on or against the weight as it travels up the ramp? Friction does work, tension does work, even weight does work. This though, because it is moving perpendicular to this force, it does no work on it whatsoever. There has to be some components of a force in the direction that it's moving in order to do work. It's D. 18. The diagram below shows a circuit connected by a student. What is the total resistance of the circuit between X and Y? So they've drawn it a funky way, but in reality, this is just a parallel circuit with 2 resistors on each branch. And we're going to have 30 and 30 and 20 and 20. So that means that we have 60 ohms here, 40 ohms here. 1 over 60 plus 1 over 40 gives us 1 over R. Let's get this to a common factor of 120, why not? 2 over 120 plus 3 over 120 is 5 over 120, and so therefore R is going to be 120 over 5, so it's going to be 24 ohms. 19. What is the reasonable estimate for the momentum of a car traveling at 10 meters per second? How heavy is a car? Let's go with 10 to the 3 kilograms. It's about a ton. So we have 10 times 10 to the 1, ton times 10 to the 3. We should have a momentum of 10 to the 4 kilogram meters per second. And finally, which is not an international system SI base unit? Seconds, Kelvin, kilograms, and coulombs. Seconds, yes. Kilograms, definitely. Kelvins or coulomb? Well, you should know that amps is an SI unit. So if amps is an SI unit, then coulombs cannot be an SI unit. So the answer is D. Question 21. A student uses the motion sensor to investigate the motion of a trolley crashing into a soft barrier. Figure 21 shows the displacement against time graph of the trolley in one experiment. The trolley has a mass of 900 grams. I'm going to turn that into kilograms. And an initial speed of 2 meters per second. It crashes into the barrier at time 0.3 seconds. So that's where it crashes. Calculate the initial kinetic energy of the trolley. Half mv squared. So it's going to be half times 0.9 times 2 squared. So that's 4, so it's going to be 2 times 0.9, so it should be 1.8 joules. B, use figure 21 to describe and explain the variation of the velocity of the trolley from t0 to t1 seconds. From t0 to 0.3 seconds, velocity is constant gradient. When it hits barrier, velocity decreases, as shown by decreasing gradient, until it comes to standstill at around, let's go with 0.8 seconds. Maybe it's a little bit before that, but whatever. Shown by flat line. Deceleration is due to resistive force of barrier. C, the student assumes that the deceleration of the trolley is constant due to the crash. Use figure 21 to determine the magnitude of the deceleration. So we're talking about SUVAT. We're looking for deceleration. We know that speed at the end is 0. We know that initial speed is 2. And we can see that the time it takes from 0.3 to 0.8. Yeah, I'm going to go with that. So that's going to be 0.5 seconds. So we're looking for V equals U plus AT. So A is going to be V minus U divided by T. And so we end up with 2 divided by 0.5. Technically it's going to be minus 2. So we end up with minus 4 meters per second squared. But it's deceleration, so they've already taken that minus into account. 22. Figure 22 shows a uniform platform secured to a wall and resting on a vertical concrete pillar. This is moments. The platform is in a horizontal position. The weight of the platform is 9100 newtons at a length of 5 meters. The center of the pillar is 3.5 meters away from the wall. Use the principle of moments and the information provided to calculate the vertical force F exerted by the pillar on the platform. Easy peasy. We only have 2 forces involved here. This is our reaction force coming from the pillar. So we can say that 2.5 times 9100 is equal to 3.5 F. So therefore, to find F, we just divide the whole thing by 3.5, and we get 6,500 newtons. The stress in the concrete pillar is that. The original length of the pillar was that. The Young modulus of the concrete is that. Calculate the compression of the pillar. So we know Young modulus is stress over strain, and we know that strain is change in length divided by original length. Let's call it X. Why not? Seeing that they've called it X. If we're dividing by that, then that means that the Young modulus is equal to stress times the original length divided by the extension, or the compression. In this case, we're looking for X, so therefore swapping E and X over, we have stress times the length divided by the Young modulus. So that is 1.1 times 10 to the 5 times the original length of 2.3 divided by the Young modulus. And that gives us a very small compression of 1.8 times 10 to the minus 5 meters. 23. A massive ball is released from rest above ground. According to a student, the principle of conservation of momentum is violated because the ball gains momentum as it falls. Explain why the student's observation is incomplete and discuss how momentum is conserved in this situation. So, Newton's third law: to every action there is an equal and opposite reaction. Therefore, force of gravity acting on ball also acts on the earth. Therefore, they both gain same momentum as ball drops, and earth moves upwards. But it's so small that we can't see it. Two balls X and Y are traveling in the same direction across a horizontal track. Ball X makes a head-on collision with ball Y. Use figure 23 to calculate the force acting on the ball during the collision. Force is equal to the rate of change of momentum. And we've been given momentum, so that's fine. The difference in momentum is 10 to 6. So that's going to be 4 kilogram meters per second. And the time taken is 0.2. So that is going to be 20 newtons. Technically minus because it's actually losing momentum, but we don't care. Momentum of ball Y before the collision is 8 kilogram meters per second. On figure 23, sketch a graph to show the variation of the momentum of Y with time t. Label this graph. So it's going to have 8 until it collides with the ball as well. We know that if ball X loses 4 newton seconds of momentum, that means that this one gains it. So it basically just does the opposite. Figure 24.1 shows a battery connected across a thermistor. Battery has an EMF 3 volts and negligible resistance. The thermistor has resistance to that at room temperature and a cross-sectional area of that. The number density of the free electrons within the thermistor is that. So we have N, and we have A, and we have R. Calculate the mean drift velocity of the free electrons in the thermistor. So we know that current is equal to ANEV, where V is the drift velocity, but we do not have current. Instead, we're given PD, it's the same as the EMF, and we're given the resistance as well. According to V equals IR, I is V. Make sure we don't get mixed up with your V's though. So PD divided by resistance equals ANEV. And we're looking for drift velocity, so let's put everything over the other side, ANE. So we have drift velocity is equal to PD divided by RANE. So that's 3 divided by 100 times 3.8 times 10 to the minus 6. Tell you what, let's just change that to 10 to the minus 4, get rid of the 100. Times 5 times 10 to the 25 times 1.6 times 10 to the minus 19. Whoops, didn't think that one through. I'm going to do the bottom bit first, just so I don't make any mistakes. 3 divided by that. And we end up with a mean drift velocity of 0.00099, or 9.9 times 10 to the minus 4 meters per second. The thermistor is now heated using a naked flame. Ooh. Describe and explain the effect on the ammeter and the voltmeter readings. Temp of thermistor increases, provides more electrons, sufficient energy to move into conduction band, therefore resistance decreases, so current increases. Of course, it's the only thing that is connected to the battery, so it's always going to be 3 volts. PD stays at 3 volts. B, figure 24.2 shows a circuit designed by a student. The cell has an EMF 1.5, internal resistance to that. The uniform wire has a length of 1 meter and resistance 16 ohms. When the contact is in the middle of the wire, the voltmeter reading is 1.2 volts. Okay, so if it's in the middle, the whole thing is 16, that means that we have 8 ohms there. Calculate the internal resistance of the cell. So we're looking for E equals IR plus IR, and we're going to factorize that. We're looking for internal resistance. We have the EMF and we have the load resistance, which is 2 and 8. So that means the load resistance is 10 ohms. But we need to find the current first. Due to Ohm's law, that's going to be V divided by R. What do we know? We know the reading here is 1.2 volts. So that's 1.2 volts divided by the resistance of 10 ohms. So it's going through. So that's 0.12 amps. Brilliant. So now that we have that, we can rearrange this to find the internal resistance. So we're going to do EMF divided by the current minus the total resistance. And so that's going to be 1.5 divided by 0.12 minus that 10. That gives us 2.5 ohms. The contact X is now moved along the wire A to B. The distance of the contact X from A is D, figure 24.8 ROS. Explain the variation of V with D in terms of the current in the circuit. So first thing we can say is that as D increases, resistance of wire increases along with load resistance. Due to this, current flowing decreases, therefore less of the EMF is lost inside the battery or cell, whatever it was, due to the internal resistance. I mean, in essence, internal resistance is just a potential divider thing. So if you're increasing the resistance of this, then it gets a bigger share of the total EMF. So there's less lost inside the battery. 25. In a ripple tank experiment, a dipper vibrates on the surface of water. Circular wave spread out. Variation of displacement of the water is shown here. Determine the wavelength lambda of the wave in centimeters. One complete wave, there to there, there to there. It's going to be 4. Explain why the intensity of the wave changes as the distance x increases. Intensity is proportional to amplitude squared. Therefore, as amplitude decreases, so does intensity. Figure 25.2 shows an arrangement used to demonstrate the interference of transverse waves on the surface of water. The dippers A and B oscillate in phase. Each dipper creates waves of wavelength 3 centimeters. C is a point on the surface of water. The distance AC is 10.5 centimeters and the distance BC is 15 centimeters. Explain what is meant by interference. We say that it's the superposition of, we better put coherent waves in there. Why not say that displacements sum at each point? State and explain the type of interference occurring at C. We are talking about path difference. Path difference is going to be, well, we have 15 centimeters, take away 10.5, and that is 4.5 centimeters. What is that in terms of the wavelength? That is equal to 1.5 wavelengths, because the wavelength is 3 centimeters. As path difference is of form n minus half lambda, waves arrive in antiphase, or pi radians out of phase, therefore destructive interference occurs. 26. A long metal wire is stretched between 2 points across a lab bench. Speed v of the transverse wave and the stretched wire is given by that. Show that the equation above is homogeneous, in other words that it actually makes sense. So the units of root t over mu is equal to kilogram meters per second squared divided by kilogram meters per second, square root of all that. Kilograms cancel. We divide by m to the minus 1, that means that we are squaring, so meters squared per second squared, and that just gives us meters per second. B. Describe and explain how you could make use of standard lab equipment to determine the mass per unit length mu of the wire. State how you would make your results as precise and accurate as possible. Use digital balance to obtain mass of length of string. The resolution should probably be to the nearest hundredth of a gram. And we're going to use a meter rule to obtain length of string approximately 1 meter long but the resolution should be to the nearest millimeter. Calculate mu by taking the mass divided by the length. How would you obtain precise results and accurate? Well, you could also ensure balance is zeroed correctly, and also reduce parallax error when measuring length. C. The stretched wire of fixed length is used in an experiment to demonstrate stationary waves. The tension is kept constant. Figure 26 shows 3 stationary waves that can be formed in a stretched wire. Frequency F of the vibration of the stretched wire for each stationary wave is shown. We know! Why do they repeat themselves so much? Use figure 26 to describe and explain how the wavelength lambda of the progressive wave on the stretched wire depends on the frequency of vibration of the wire. So, as tension is constant, wave speed is also constant. And okay, as is mu, because it's the same piece of wire, isn't it? Therefore, due to V equals F lambda, F is inversely proportional to the wavelength, or it should probably be the other way around. Wavelength is inversely proportional to the frequency. And let's give an example. For 20 Hertz, lambda is equal to 2 lengths of the wire. For 40 Hertz, wavelength should, if the frequency has gone up, then that means the wavelength should have gone down. Sure enough, it has. We can see we got one complete wave. So that makes sense. 27, a researcher is investigating the work function of metals using a photoelectric effect. And we have threshold frequency and work function. Explain what is meant by threshold frequency. The frequency above which photons have sufficient energy to overcome the work function phi and liberate electrons from surface of metal. Figure 27 shows the data points for metals A, B, D, and E. What about C? Use Einstein's photoelectric equation to show that phi equals HF0. So E equals HF minus phi. When F equals F0, electrons have EK of 0. Therefore, HF0 equals phi. Plot the data point for C on figure 27 and draw the straight line of best fit. So C has a threshold frequency of 6.5 and phi is 2.7. So it should be bang on there. Line of best fit. Finally found my ruler. Use figure 27 to determine the experimental value for H. So we know that from this that H is equal to phi divided by the threshold frequency. So therefore it's going to be the gradient of the graph. So let's pick some nice points. Let's go from 2.1 and 5 to 8 and 2 and 3.5. So that's 3.5 take away 2.1 divided by 8 and 5. So that's going to be 1.4 divided by 3. But of course this is in electron volts and this is times 10 to the 14. But we need to turn this into joules. So let's times that by 1.6 times 10 to the minus 19. So 1.4 times 1.6 times 10 to the minus 19 divided by 3 times 10 to the 14. And I have 7.5 times 10 to the minus 34. Mark scheme says 7.4 is the maximum, so it seems like my gradient is a little bit too high, but I think that's a bit mean. Explain without doing any calculations how you could use figure 27 to determine the percentage uncertainty in H. We draw a line of worst fit, calculate percentage uncertainty using difference between gradients divided by the gradient of line of best fit times 100. So that's it. I hope you found this helpful. If you did, please leave a like. And if you want to go into paper 2, click the card and I'll see you there. Bye for now.